the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for those students who are going through linear algebra right now and are currently in matrix equations. This is the last hurrah within this topic before we move on to the next topic within linear algebra. In this video, we're just going to spend a few moments, actually not very long, proving a single little theorem. This theorem is all about the product of matrices and vectors, specifically the properties of those products. And so we're just going to choose one of these here. The reason why I'm choosing to do this example is because I'm going to show you how you as a student would prove one of these properties, because you'll likely be asked to do that on an exam or a quiz or something like that, or for a homework in your linear algebra class. These are generally kind of easy to get, or easy enough to get for a linear algebra student, that they are assigned by professors. So let me showcase what your professor is going to expect. Given an m by n matrix and two vectors u and v in Rn and a scalar c, the following statements are true. The matrix A times the quantity u plus v is equal to A times u plus A times v, and likewise A times the quantity, the scalar c times u, is the scalar c times the quantity A times u. Now, that's a lot to say. It's actually much easier to prove than to say. It doesn't really matter to me which one of these that we do. What's important is that we just choose one and go with it. I think I'm going to leave the more challenging one to you as a student. They both are actually almost the same as far as proofs go. So let's go ahead and prove part B. I want to showcase the mindset of this. So you're going to start with the fact that A is an m by n matrix. And look at the other structures within the claim that you want to prove. For example, C is a scalar and U is a vector in Rn. So I will go ahead and make those claims as well. Now, because you don't know the entries of the matrix A, nor do you know the entries in the vector U, you're going to create a sample of what those are going to be. Now, I don't mean a sample as in, oh, a matrix A could be 1, 5, -3, 2, blah, blah, blah. No, you're going to keep it as general as possible. So we'll go ahead and say it this way. Now, if you take a look at that matrix right there, notice how I've used subscript notation intelligently. For example, A sub 1, 1 means first row, first column. A sub 1, 2 means first row, because I'm still in the first row of A, but now second column. And so on and so forth down the line for that row, until I get to first row and the nth column. Then you do the same thing for the second row. A sub 2, 1 means second row, first column. And A sub 2, 2 means second row, second column. And this notation is actually going to be used in your linear algebra course for later topics, so you might as well get used to it now. A sub 2n means second row, nth column. And you can see it goes all the way down to the mth row, first column, mth row, second column, all the way to the mth row, nth column. That is the most general form of an m by n matrix that you can possibly make. And we'll also let u be the vector u1, u2, all the way to un. Now, to be very honest with you, you might not even need this matrix structure for this specific proof, because we have another way of writing a matrix right now. We could have written that matrix A as A sub 1, A sub 2, and so on and so forth until you got down to A sub n. That's another way we could have written that. And in fact, I might actually just use that in this proof. But in future proofs, you might have to use this version of A. But we'll actually stick with this column vector version of A for this proof. And you would also for proof A as well, technically. Now what we're going to do is start on the left-hand side of B here. We're going to take the matrix A and multiply it by the scalar multiple C times U. Now you cannot make any assumptions. Like you cannot say, oh, therefore C moves out front. No, you cannot make that assumption. You do not have a rule or a theorem right now that stated, oh, a matrix A times 5 is 5 times the matrix A. Nobody ever told you that. So you cannot use that. This is what I referenced early on in a linear algebra course, or our linear algebra course, or one of my linear algebra videos, is that the hardest thing about linear algebra for students initially is the baby steps. And so here we're going to perform baby steps. The matrix A times the quantity C times the vector U. Well, I'll start with the fact that I'm going to call the matrix A the column vector A1 but then the column vector A2 all the way down to the column vector A sub n. And C times the column vector U looks like that. Notice I haven't actually done anything. I just rewrote the matrix A as a bunch of column vectors and the column vector U as, well, its component form, column vector. Now I do have one theorem I can use. I have a theorem called the scalar multiple of a vector. So I could take this scalar multiple and apply it to each entry within this vector. That's one theorem that we can take advantage of. So I'll go ahead and do that right now. And we get down to this point right here. Again, performed a perfectly legal move. The next perfectly legal move is the fact that a matrix times a vector, we know from definition that a matrix times a vector is going to be a linear combination of the columns of the matrix, where the weights of that linear combination are the entries within the vector. So this is going to be the linear combination CU1 times the vector A sub 1 plus CU2 times the vector A sub 2 plus ... plus CUN times the vector A sub n. And we get all the way down to here. Now, the thing you have to wonder is where you need to go. Look back at what we're trying to prove. We're trying to prove that the matrix A times CU is the same thing as C times the matrix vector product AU. Well, notice that C on the right-hand side there is factored out. And now that we've gotten to this point right here, it's just a linear combination, and there's a scalar in front of every single one of those terms in this addition. I can always factor a scalar out. We know this actually from the arithmetic properties of vectors. There's an arithmetic property of vectors that says the following: C times the vector U plus the vector V is the same thing as C times vector U plus C times the vector V. That is, if I see a common constant in front of the sum of vectors, I can factor that common constant out. And so that's what I'm doing here. I'm going to factor out a common constant C. I'm left with U sub 1, A sub 1, plus U sub 2, A sub 2, plus so on and so forth, all the way down to U sub n, A sub n. But this piece I'm highlighting right now is a linear combination of the column vectors of A. The weights of that linear combination are U1, U2, all the way to UN. So this is just another way of writing the following. We're kind of working backwards a little bit on that, right? So normally we would say, oh, the product of this matrix and this vector turns into this linear combination. But you can go in reverse too. If you have a linear combination, you could write it as the product of a matrix and a vector. Well, that's the product of the matrix A and the vector U. Notice what I've just arrived at. I started at A, the matrix A times the quantity CU, and I've ended up with C times the quantity matrix A times vector U, which is exactly what I wanted to prove. So notice how patient I was in that work. I did write out this matrix up here and I didn't actually need it, But again, I like to write that every once in a while just to remind you that that is a structure that you're going to have to get used to as you move through linear algebra. Luckily, we didn't need it because it is kind of a pain to use if you have to use it. However, every step along the way, I'm really using previous theorems, like this red ink right here. That was just a distribution of a scalar into a vector. We know that from a previous theorem. And then the next step down, well, that's just cleaning that up. We just multiplied scalar times vector. But the next step after that is a matrix times a vector, and we had a definition. A matrix times a vector is just a linear combination of the columns of the matrix with the weights of those vectors being the entries within the vector U, or in this case, CU. And finally, we have a theorem, which is associated with the arithmetic properties of vectors, which just tells us that you can factor out common factors off of a sum of vectors. So the common scalar factors, I should say. So I factored out the common scalar factor C. I'm left with this highlighted business here, which is actually just a linear combination of the columns of the matrix A with weights U1, U2, all the way to UN, which is a matrix vector product. And that was bothering me. And that can be written as C times the matrix A times the vector U, and we're done. All right. So those little baby steps, please, 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 please get used to them, because those are very typical styles of problems to be given on an exam or a quiz, just so that your instructor knows you are patient enough to do the baby steps. All right, I hope this video is helpful, and I hope you have a wonderful day. Take care.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.